So we will have an exam on Friday. It will include power series from chapter 9, which you haven't been tested over yet. We'll include all of chapter 10, and it will include this material on vectors up through and including lines and planes in space. Okay? But section 6 and 7 is something that won't appear until the final. I'm telling you, you may loathe my guts at this point, but you'll thank me later. You might be 40 when you thank me, but you'll thank me. You'll thank me when you. I think you'll be thanking me when you go to study for the final exam, because you will have already boosted significantly your study paradigm for the Calc 2 final. Okay. Of course, you know, I'm going to have to see what happens between now and Friday in terms of quarantine stuff. There's still people being quarantined and not quarantined, but we'll see. Okay. All right. So, hey, let's try, if we can, let's try to finish this stuff about lines and planes. Now, remember, we had the line situation, which was back here. We didn't just have the parametric equations. Really, we also had the so-called vector equations of a line, which were kind of written this way. X, Y, Z is equal to X1, Y1, Z1, thought of as a vector, plus any multiple of the direction vector ABC, yeah? And then from that, we got the so-called parametric equations by equating X, Y, and Z coordinates from the vector equation, yes? Sort of distribute the T through and say, well, X has to be X1 plus AT. And then from this, you got the symmetric equations by doing what? Solving for T. Yeah, by solving for T. And you might say to yourself, man, those symmetric equations feel sort of mysterious, like there's two equal signs. What's going on? Well, essentially what you do is you when you have the symmetric equations is you say, I get to choose one of the variables, like Z, for instance. Like I could put Z equal to 5 in there, right? And if I put Z equal to 5, then the X and Y values would have to be determined based on that. Because if I plug like 5 in for Z, then I'm going to get a number right here, correct? And then basically that's going to force the values of X and Y, yeah? Because at Y minus Y1 over B would have to be equal to that same number. And so would X minus X1 over A. So you could figure out what X and Y would have to be in response to what you set Z equal to, okay? So that's how this kind of works. What's interesting is it looks like you basically have one independent variable and two dependent variables. Like one of the variables is independent, you could let it be whatever you want, and the other two have to respond accordingly, okay? All right, so vector, parametric, symmetric equations of a line, okay? Then we had the standard equation of a plane. This equation right here came from sort of taking the dot product of the normal vector. Remember, normal vector means perpendicular to the plane, yes? Okay, and you had a point in that plane, and essentially the picture that we had was something like this. So here's, right, here's N, here's this point P, and then what we did is we went to any other point Q, and we said, hey, those guys are going to be perpendicular. That is, N dotted with PQ is going to be what? 0. And that, my friends, is what gave rise to that standard equation of a plane. And then when we distribute this A, B, and C through, that's what gave rise to the so-called general form of equation of a plane, okay? You kind of combined the AX1, BY1, and CZ1 with the minus sign, and that's what became your D, okay? Like D is equal to negative AX1 minus BY1 minus CZ1. Okay, that's what D is. this D right there, okay? Here was a picture that we were using, right? I mean, it gave rise to the other standard equation of a plane. And that stuff is pretty interesting, but there's some other stuff going on under the hood that I want to talk about today for sure. Okay, so we did some examples last time, but I want to talk about this. What if I have two planes? Okay, two planes in space, there's only two options. Just like if I had two lines in two-dimensional space, that is in the XY plane, those two lines are going to do one of two things. Either they're going to be parallel. By the way, parallel even, I guess, technically speaking, parallel would mean that they're the same line, but let's just pretend they're two different lines, okay? Okay, two lines in the XY plane are either going to be parallel or they're going to intersect, yes? In three-dimensional space, it's more complicated with lines. In three-dimensional space, two lines are parallel. By the way, you can easily tell if two lines are parallel by simply looking at their direction vectors. What would have to be true about their direction vectors for two lines to be parallel? The direction vectors would have to be parallel, which means the one direction vector would have to be a multiple of the other, yeah? Okay, so, but there's a couple of other options. Two lines could be parallel, two distinct lines could be parallel, two distinct lines could intersect in three-dimensional space, yes? But there's a third option. They could so like I could have two lines that are parallel like this, or that intersect like this at a point. I could have two lines that are parallel, but there's actually a third option, which is kind of weird, right? So I could have one line like this, and I could have another line that kind of comes underneath it like that. Let me use blue here just to make it clear. I could have another line that kind of goes like that in three-dimensional space, yes? And you call these lines, this is kind of a new thing, you call these lines skew. Okay, they're skew lines. It's a way that they're not, that they could be not intersecting while at the same time not being parallel, yes? I mean, these two lines are not intersecting, but they're also not parallel either. Okay, does that picture kind of make sense? It's like my arms, one's kind of floating above the other one or something like that. So there's a third option for lines in three-dimensional space. But if I talk about planes, there's still only two things that can happen. Planes either are parallel, yeah, or they intersect. And actually, they intersect not just in a point now. What do they actually intersect in? When two planes intersect, they intersect in a line now, right? Okay. And I might be interested in the angle between these two planes. But we have something, if we have a plane, by the way, normal vector means perpendicular vector. Where did we see, okay, let me clear this out. Where did we see, like in this equation right here, where do we see, if I were to kind of write the plane in its standard form or in its general form, where do we see the normal vector pop out? Like if someone just handed me an equation of a plane, where could I just immediately extract the normal vector for that plane? A, B, and C, it's right here. Yeah? So these three things give rise to the normal vector, ABC, okay? You know that's the coefficients of X, Y, and Z respectively are going to be a normal vector for that plane. That's important. Okay, so somebody gives me a plane, somebody gives me another plane in equation form, I can immediately extract their normal vectors. And if I want to measure the angle between those planes, by the way, there's going to be a couple of options for angles. Okay, oh man, I don't know about this. I'm starting to regret this. Okay, so hey, oh, that doesn't look too bad. Okay, so like this angle right here would also be theta. Well, what about this angle right here? What would that be for these two intersecting planes? Yeah, that'd be pi minus theta. And of course, this down here would also be pi minus theta. So one of the angles is always going to be smaller than 90 degrees. Do you understand? So you always kind of pick out the angle that happens to be smaller than 90 degrees. And you call that the angle between the planes. Okay? Now we're kind of playing fast and loose with things here, but one way that you can get the angle is by looking at the two normal vectors. Like the angle between the planes, you think about it, if two planes start out on top of each other and one starts to peel away, then the angle between the planes is going to be the same as the angle between the two normal vectors. Yes? You can kind of see that that's going to be what happens. Now, there's one thing here I want to be careful of, because this vector could, in theory, be going the other way, in which case the angle between those two things is like bigger than 90 degrees. Yes? Okay? So you do have to be careful about that. But this picture is simply supposed to be illustrating that we can get the angle between two planes by looking at the angle between the normal vectors. That is going to tell us at least one of the angles between the planes, yes? And we could always get the other angle from that one. Does that kind of make sense, hopefully? Yeah? Okay. So find an equation for the angle between the normal vectors, which would also be the angle between the planes potentially, yes? Okay, well, all right. So isn't it true that N1 dotted with N2 is equal to, okay, so what's one of the equations that we've come up for the dot product of two vectors? We had two. One of them was easy. You just multiply the coordinates and add those together. But we had another version. What was it? Yeah, the magnitude of N1, magnitude of N2, cosine of the angle between them. Yeah? Therefore, you know that cosine of the angle between the two vectors is equal to N1 dotted with N2 over the length of N1 times the length of N2. Okay? Could that angle be greater than 90 degrees? Could that angle be greater than 90 degrees? Yeah, it could be, yeah? What could I do to guarantee, though? Because remember, like, cosine of an angle, that could be negative, correct? Couldn't I get the complement of that angle? Or not the complement, the supplement of that angle by actually flipping across the y-axis in the unit circle. Do you see what I'm saying? So like, think about this for a minute. Okay, so suppose this was my angle right here. I don't know, like alpha. Okay, then the cosine would be this thing right here. This would be cosine of alpha. Do you see what I'm saying? Yeah? But what if I took this angle right here? Let's call this angle beta or something, okay? Alpha plus beta is equal to 180 degrees. Do you see what I'm saying? Alpha plus beta is equal to pi. Well, what if I were to flip that, or kind of instead of looking at alpha, I looked at the angle beta. Okay, so this is the angle beta right here. Okay. Then this right here, my friends, isn't that cosine of beta? Yeah? Yeah? And incidentally, aren't cosine of alpha, so think about it, cosine of alpha and cosine of beta, how are those going to be related to each other? Are they equal? No. How are they related to each other, though? One of them is the negative of the other. Yes? One of them is the negative of the other. Okay? So, How could I get the angle to always be between 0 and 90 degrees? Yeah. And then this theta right here is guaranteed to always be between 0 and 90 degrees. Okay? Then that angle is always guaranteed to be the one that happens to be smaller than 90 degrees. I think that's kind of cool, right? You can kind of flip the situation around just by thinking about how cosine works, okay? So you take the absolute value of the dot product of the normal vectors. And then that theta will be the angle that happens to be smaller than 90 degrees. I think that's cool. Okay, so here's kind of the formula. That's why that absolute value is there, because it guarantees that 0 is equal to or less than theta is equal to or less than 90 degrees. Okay? Cool. All right. So, what if the dot product of N1 and N2, oops, those aren't supposed to be caps. It's because of the font we're in here, right? So this is little n, and this is little n and little n. Okay. What if the dot product of the two normal vectors is 0? What does that tell you about the planes? They're perpendicular, yeah? They're perpendicular, yeah. Okay. By the way, so watch, let me think about an example with you on this one. So for instance, the XY plane, how would I notate that as a plane? What's true? Think about it. So the XY plane means anything in the XY plane. That's where we've kind of been working up until we moved into the third dimension, yes? What's true about all the Z values there? Z is always, if you're in the XY plane, Z is always 0, which, by the way, if I want to write that in standard form, I would say, okay, that's 0x plus 0y plus 1z equals 0. Okay, the D value is actually 0 there. So what would be a normal vector for this plane? What would be a normal vector for this plane? 0, 0, 1. What's that vector called? Oh man, what did I just do? Sorry. Oh, undo. Whoop. Okay. So K, yes, thank you. Okay, K, which is, by the way, 0, 0, 1. Does it make sense that K would be a normal vector for the XY plane? It certainly does. Okay, what about the YZ plane? Okay, what would be the equation of the YZ plane? If I'm in the YZ plane, what's always 0? So you guys know what I'm saying here. So, right, so here's X, here's Y, here's Z. I'm talking about this plane over here, yeah? Yeah? So what about the YZ plane? What's always true about that? X equals 0. And what does that translate to if I want to write it in standard form? 1x plus 0y plus 0z equals 0. So what would be a normal vector for this guy? I. Don't you see? Yeah? And that totally makes sense that I would be a normal vector. You stare at that for a minute, right? So here's I right here. Yeah, and that would be a normal vector. Okay? Now, what's true about the XY plane and the, what's true about the XY plane and the YZ plane? What's the angle between those guys? So there's the XY plane, there's the YZ plane. What's true about those two guys if I think about the angle between them? Look, it's 90 degrees for crying out loud, right? Yeah. And what's true about the dot product of this, of, you know, N1? So if I take N1 dotted with N2 here, okay, that's going to be K dotted with I. Of course, K dotted with I is simply 0, right? And so I would get cosine of theta, the angle between these things, is equal to 0. And what angle between 0 and 90 degrees is such that its cosine is 0? What would that tell you? I'll tell you that theta has to be pi over 2. Yeah. So that's interesting. What if the dot product of the normal vectors is 1? What does that tell you? What if the dot product of the two vectors is 1? Huh? Theta is 0. Is that true? What, say again? Okay, if the dot product is 1, what would happen? So if the dot product was 1, then I would get cosine of theta equals 1 over the length of N1 times the length of N2, correct? Okay. Can I really say much of anything? Can I say anything at all? The answer is no. The reason I brought this up was because I constantly see students, I don't know why, I'm just bringing this up, okay? I don't know why this happens, but I feel compelled to bring it up because students all the time think that when the dot product is 1, that somehow that means something, either that the planes are like parallel or they're perpendicular. Does that make sense? Okay. So it's not true. So what, let me just ask you a question. What, if the angle was 0, what would you get? Well, what would that mean? The angle being 0 between the planes would mean that the cosine was 1. Does that make sense? And so you would get 1 equals to the dot product or the absolute value of the dot product over the length of the products of the lengths. Okay, so what you would get in this case is you would see that the absolute value of the dot product would have to be equal to the product of the lengths. And that's really all you can conclude. You just have to be cognizant. You have to be aware of what the lengths of each one of the normal vectors is. And if the dot product is literally equal to the product of the lengths, you know that you have two planes that are parallel to each other. Does that kind of make sense? Okay, hopefully. Okay. Well, what that means is you're dealing with the same plane, actually. What's another way that I could tell that two planes were parallel and they weren't the exact same plane? Like two planes are parallel, they actually don't intersect each other. How could we tell that two planes were parallel to each other? What would have to be true about the normal vectors? They would have to be parallel, yes? If two planes are parallel, their normal vectors would have to be parallel, which means that one normal vector would have to be a multiple of the other, yeah? Okay, so be warned, this guy right here doesn't really tell you much, okay? But this one does. This tells you that the planes are perpendicular, okay? How to sketch a plane in space, okay? I kind of showed you this last time, but I want to show you again, okay? I'm going to actually sketch this by hand, okay? Just so you can see that it can be done, right? So here's this, right? There's the negative y and the negative x-axis and the negative z-axis, okay? 2x plus 3y plus 4z equals 12. Remember what we did last time? Didn't we just start plugging in some numbers, like made 2 of them 0 and figured out what the third one had to be? That told us where this thing was intersecting the coordinate axes. So for instance, if I put x and y equal to 0, what does z have to be? 3. Okay, so that means I would have 0, 0, 3 on the plane. Okay, And let's see, let's try some other things. Like what if I put y and z equal to 0? What would x have to be? 6, yeah. Okay, so then I'm gonna put this guy out here at 6. Okay, so that's another point on the plane. Okay, and then finally, what else could I make equal to 0, I guess? Yeah, how about x and z? Yeah, yeah. X and z being 0. What's y going to be? 4. So that means 0, 4, 0 is on the plane. Okay. So I don't know, maybe 4 is right here. Okay. So let's see. There's kind of a depiction of a portion of that plane. You guys understand that's not the whole plane, yeah? But that's a little snapshot of the plane itself in three-dimensional space. Okay, it's oftentimes helpful to draw this little triangular portion of the plane that happens to be where the plane hits the x-axis, y-axis, and the z-axis. Does that make sense? Does that picture kind of make sense? I just picked out 3 points, and the points on the coordinate axes are going to be ones that aren't collinear, and thus will make like a little triangle in the plane. Of course, it's a little bit different if a plane doesn't happen to hit one of the coordinate axes, yes? If the plane doesn't happen to hit one of those, then you would have to think differently about that, okay? If one variable doesn't show up in the equation of the plane, this is what I'm asking about here. What if one variable doesn't show up in the equation of the plane? Okay, so for instance, what if I had something like, 2x plus 3y equals 6, okay? Then what? What's up with that? Well, then z is free. Yeah? Z can do whatever it wants. X and Y are bound by this equation, correct? But then wherever X and Y are, Z can be anything at all, okay? So the way that that's going to play out is when we go to sketch this, watch. So let me just say, okay, here's X, Y, and Z. So look, I'm just going to sketch a couple of things. For instance, if X is 0, then what's Y? 2. So that means like 0 to anything, right? 0 to any Z value is going to be on the plane. Does that make sense? So 0 to, okay, so here's the point 2, anything, and really, you understand, I could, anything at all, like any Z value at all is going to be legitimate, yeah? So I can kind of go like that, okay? Now what about, so let's think about some other value, or let's think about what happened if I put a Y value equal to 0. What would the X value have to be to make this equation true? 3, okay? All right, so 3, 0, okay? 3, 0 is on there, but so is like I could let the Z coordinate be anything at all above or below this point. Okay? So like this right here is the collection of points. This right here is the collection of points 3, 0, Z, where Z could be anything. And this right here is the collection of points 0, 2, Z, where Z is allowed to be anything, okay? So you know, by the way, that anything on this line, 2x plus 3y equal to 6, after all, is a line in the xy plane, correct? And just like like any point on this line is going to be a point on the plane, but so is any Z value above and below that, yeah? So what is the equation of this plane going to look like? Or what's the depiction of this plane going to look like? Well, it's going to look like this. Okay. That's the stuff below the XY plane. Yeah. So this thing just goes straight up and down, and it has as its shadow in the XY plane this line, 2x plus 3y equals 6. Yes. So 2x plus 3y equal to 6 is kind of the shadow of this plane in the XY plane. It's what the intersection of the plane is with the XY plane. Okay, it's that line. Does that make sense? Hopefully. Okay. So that's what's going on if you happen to be missing a variable. That just means that that variable is free. And so it can just go wild while the other things are bound to the equation itself. Okay. Any questions on that? I think that's kind of neat to think about. Finding the distance between a point and a plane and a line is the place we're going to go next. Okay, we want to find distances between points and planes and points and lines. Okay, so let's do it. Finding the distance between a point and a plane. Okay, so here's this point Q right here. Okay, this point right here is Q. And I want to know the distance from that point down to the plane. From that point down to the plane. Now remember, if I'm in a plane, I will have a point P and I will have a normal vector N. Yes? Okay. A point P and a normal vector N. Well, what you can do is you can actually compute the vector from P to Q. And then if I want this distance right here, what I really should do is project that vector onto the normal vector. Okay, here's the normal vector over here. Okay, if I project that onto the normal vector, do you guys see that that will actually be the distance? The normal vector is much bigger than that. It goes all the way up to here. Do you see that? But if I project that vector PQ onto the normal vector, I will get the distance. You see what I mean? We have a formula for projection. Right? So we project PQ, we take the point in the plane, we go up to Q. Okay? The length of PQ is not the distance necessarily, right? I mean, it could be slanting off. The vector could be going from P slanting over to Q. The distance needs to be perpendicular distance. And the way we do that is by projecting PQ over onto the normal vector. Yeah? And so the distance is going to be the length of the projection. The length of the projection. Find this distance by projecting the vector PQ onto the normal vector N. Sorry about this. This thing keeps replacing little n with capital N. Okay? Does that make sense? So you want to know the distance between a point Q and the plane. Take a point in the plane, form a vector, and project that vector onto the normal, and you'll have it. Yeah? You just take the length of that projection, and you've got it. Okay. And you guys, of course, remember, do you remember the formula for projection, right? We kind of have that in our cognition at this point. Okay. All right, so here it is. Distance between a point and the plane. Here's the formula. It's just the length of the projection of PQ onto N. Where Q is the point and P is a point in the plane. And of course, the formula for that projection, remember, we had the projection of U onto V. Okay, that was equal to U dotted with V over the length of V squared times V, okay, times V. And so if I compute the length of the projection, if I compute the length of the projection, how would I get that? Well, you know, look, U dotted with V is just length of U, length of V, cosine of the angle between. okay? And of course, if I take the length of V itself over the length of V squared, that's just going to leave a single factor of the length of V downstairs. Okay, so absolute value of U dotted with V is what you would have upstairs over just a single factor of the length of V. Because if I take the length of that projection vector, one of the factors of the length of V is going to cancel. Okay. And by the way, I mean, you may remember that this is just the length of U cosine of theta, cosine of the angle between the things. Of course, I have to take absolute values of this. Okay. That was how we computed the length of the projection. That was one of the first things we did when we tried to come up with a formula for the projection of one vector onto another. Okay. Remember, so this, like, I mean, here, let me just draw this picture so that you have it in your cognition. So here's U, here's V, okay? Here is the projection of U onto V. Okay, this right here would be the length. This would, right, and here's the angle between these things. This would be the length of the projection of U onto V. Yes? How would I get that? What trig function would I use? I have that right triangle, I have the hypotenuse, and I have the adjacent side, yes? Right, so you would have that the length of the projection of U onto V is equal to, right, that's the adjacent side, is equal to the hypotenuse cosine of theta, okay? Hypotenuse is length of U, cosine of theta. And of course, we take absolute values to make sure everything inside is positive, right? So that's basically where this thing is coming from right here, yeah? Okay. But this is usually the thing that's easier to remember. Just take the absolute value of the dot product and then divide by the length of n, and you'll have the distance between those things. Okay, any questions on that? So that's distance between a point and a plane. You just take the point, point in the plane, go out to that point, project that onto the normal vector, and that will give you the distance. The rationale is pretty straightforward for why that should work. So let's do an example. So let's do 2x plus 3y plus 4z equals 12. Okay, so that's a plane. And let's do q equal to, I don't know, let's do 1, 2, 1. So I want the distance, e equals to the distance between Q and the plane, okay? Okay, so how would I find that? What do I need in order to find that? I need a normal vector. What's the normal vector, Daniel? Yeah. So those three things tell me what a normal vector is. It's just going to be 2, 3, 4. What else do I need? I have my point Q, but what else do I need in order to talk about projection onto the normal vector? I need a point on the plane. Can you think of a point that happens to be on the plane? Don't think too hard. 0, 0, 3, that would be fine. So P equal to 0, 0, 3 is on the plane. Okay. P equal to 0, 0, 3 is on the plane. Okay, that's cool. So then I have to form the vector PQ, which is, okay, remember you go basically terminal point minus initial point. Okay, 1 minus 0, 2 minus 0, and 1 minus 3. Okay, so I get 1, 2, negative 2. Yes? And so what's the distance going to be? Well, it's the length of the projection. Length of the projection of PQ onto N, which we have already determined is going to be the dot product of n and PQ in absolute value divided by the length of n. Okay? So what is the dot product of n and PQ? Well, I have to take the absolute value. So it's going to be 2 times 1, which is 2, plus 2 times 3, which is 6, minus what? Minus 8, okay, over the length of n, which is, I mean, the square root of what? 4 plus 9 is 13. Is that right? So 4 plus 9 is 13 plus 16 is, 29. Well, what's the thing? What's the deal? What do we get here? 0. What? This is saying that the distance between this point and this plane is 0. So apparently Q is on the plane. Q is on the plane? Well, yeah, because think about it for a second. What if you plug in 1, 2, and 1 in for X, Y, and Z? That would give us 2 plus 6, which is 8, plus 4, which is 12. And so it is indeed on the plane. So right, our little distance formula actually caused that to happen automatically. I think that's pretty cool. Yeah? All right. So, any questions on that? By the way, the fact that we got 0 tells us that the normal vector and the vector PQ were actually perpendicular. Yes? The dot product was 0, which is exactly what should happen if I have a point that's in the plane. If I go from one point in the plane to another point in the plane and form a vector, the normal vector is going to be perpendicular to that. Yeah? That's exactly what ended up happening. Any questions on that little example? Okay, what about the distance between a point and a line in space? Ooh, that's interesting. What about the distance between a point and a line in space? Well, I've written down this, remember, so like, if I go back a couple of slides, there it was the absolute value of the dot product divided by the length of n, yes? The dot product of PQ and n divided by the length of n, yeah? Here, it's PQ not dotted with n, okay, but crossed with not the normal vector, but here I'm talking about a line, so I'm going to be dealing with a direction vector, yes? So it's PQ crossed with the direction vector, the length of that, divided by the length of the direction vector, which, by the way, if you think about this for a second, here's PQ, here's U, right? Remember, the length of the cross product is length of PQ, length of U times what? Sine of the angle between those things, yes? And that would be divided by the length of U. So in the end, these length of U's would cancel, okay? And so apparently, the formula for distance between a point and a line is simply PQ times sine of the angle between the direction vector and this vector PQ. Now let's kind of see why that happens to be the case. Okay, so there's my line. Okay, here's my direction vector. Okay, here's my direction vector U. Okay, here's my point P right here. Okay, here's my point P. And what I'm saying is I want some kind of point Q. I want its distance from this line. Well, what we do is we actually form the vector PQ. Okay. And what we do here is we should probably do something similar to what we've kind of done before. We want this distance right here. Okay, so here's the distance. Okay. Now you tell me, if I call this angle right here, theta, between U and PQ, and I want this distance over here, that's the opposite side. So what trig function would I use? Sine. You know that sine of theta is going to be opposite, which is d, over hypotenuse, which is what? The length of the vector PQ. So in other words, d is equal to the length of the vector PQ times sine of the angle between them. Yes? Which is exactly, my friends, what we see right here. Yeah? And then it's just a matter of making this more convenient for computation. So you multiply and divide by the length of u. Why? Because I want to see the length of the cross product kind of fall out of this. Yes? So you compute the length of the cross product between PQ and the direction vector, and then you divide by the length of the direction vector, and you will have the distance, which I think is interesting for sure. Okay, any questions on that? Length between point and a plane has to do with the dot product. Length between a point and a line has to do with the cross product. It's kind of interesting that there's a nice interplay. One of the two products kind of shows up in each one of those. We'll do an example of this tomorrow. I'll stop right now.